It's my great pleasure again to welcome you to the CITP seminar. We're delighted to have Professor Maria Apostolaki here. Maria started at Princeton in the fall semester after finishing her PhD at the ETH in Zurich, and also completing a postdoctoral stint at Carnegie Mellon University. Her research interests are very broad and touch upon some key areas at Princeton, including security and privacy, but also network performance, which is the subject of her talk today. She's also a steering committee member of our brand new D Center. I think one of Maria's groundbreaking results was to show how insecurities in internet routing could be used to compromise the security properties of cryptocurrencies like Bitcoin, including potentially leading to double spending attacks. But she's also done an incredible amount of work on performance aspects of network systems. And in her talk today, she's navigating interesting policy questions about how relatively smaller autonomous systems could regain power in a hierarchical internet setup and enhance the performance of their networking ecosystem. So Maria, thanks so much for taking the time to be here. One quick announcement I want to make to the CITP community is that in the spring semester, we are also, in addition to our Tuesday seminar series, we're also starting a distinguished lecture series. You also have a poster back here on the whiteboard with John Kleinberg on Wednesday, February 15, being our first speaker. So please, thanks. The floor is all yours.
All right. Hello, everyone. Thanks for the great introduction. I very much appreciate it. I first want to share that I'm extremely excited to be here today. I was always admiring what CITP has accomplished, like the vision, the efforts. It's extremely inspiring. So I want to start this talk with a question. What do we actually want the internet for? Well, what do we use it for, right? And the reason I'm asking this question is that we often forget and we neglect to understand how critical infrastructure runs on top of the internet, how much we rely on the internet for our everyday life. And these are just some applications that come immediately to mind. For example, we do live streaming, everything we watch, the way that we get informed, we learn, everything is live streamed, and we use the internet for this. We also do video conferencing that has lately basically displaced the way that we work, because we work remotely. So Zoom video conferencing is the go-to for working. And we also, of course, we do online shopping. We access our banking infrastructure using the internet. We potentially maybe participate in online auctions. We might be using cryptocurrencies. We might be using cyber physical systems, or our house might be doing that, or we have a lot of real-time applications. So what I'm trying to help you understand here is that everything we do in our everyday life kind of depends on the internet and depends a lot on the performance, on the security that the internet provides. So taking into consideration that we rely so many applications and important infrastructure in the internet, we should have some requirements, right? So what do we actually want from the internet? Well, I would say basic stuff, I want low latency, I want throughput, I want some consistency, privacy, and potentially I have some more advanced properties that I want to enforce, like geofencing. So low latency will help me when I'm talking to a friend that we can actually talk and we don't talk to each other on top of each other. Throughput will help me because if I'm watching a game or I'm watching a movie, I want this to actually not stall all the time and make me mad. Consistency is important. I'm not fine with now I have very good quality of service and just in few seconds it stops. Privacy is really important. I'm not sure why we expect the internet to provide this, because it doesn't, but this is another. We do expect though that as our traffic is routed over the internet, they're not just random entities that we're not aware of. They just look at their traffic, we analyze it, they know what we're doing. I don't know why we have this assumption, but anyway, this is something we would like, right? And geofencing is potentially we don't want the data that we are exchanging to be spread across the world. We only allowed it to do its a subset of the world potentially. So I really hate to break the news to you, but actually the internet does not provide anything. And what's important is that the internet was not made to provide all of that. It was not in the design decisions because that was not the goal. The internet is a best effort service. That means that all the routers, so all the network devices that are there to route our traffic from one point to the other, the only goal and the only promise that they make is that they will do their best to route our traffic. That's it, nothing else. They don't say anything about privacy, anything about security, anything about performance even, right? So that naturally will, like we have basically, we have two, we have different objectives and completely different reality, right? So we expect different things, but the internet was never made to offer this. So this kind of looks like super pessimistic. So it's kind of counterintuitive. Why would I come here to tell you that? Well, actually, somewhat good news could be that we have paid service for all these things, right? Every time the public infrastructure doesn't work well, of course, that's a great business model and we'll have paid service for that, right? So for example, we have VPNs, we have network as a service, and we also have servers that are brought at the end. So let's look at each of those solutions and see what they offer and potentially what they don't offer, or what is the penalty for using them. I want to start with virtual private networks and VPNs, because I think that most of you would actually have used those. So VPNs are mostly for privacy, and what they will basically help, like if you are in an untrusted network, you can use a VPN to prevent entities in the middle of the internet or in the rest of the network to actually profile your traffic or learn anything about your traffic. So it kind of hides your identity. And it's very easy to use, like everyone can just download a VPN, potentially pay for it, but it's easy to use and we have all used it. But on the other end, we have performance issues. And that's because all our traffic has to be routed through a central point. And that basically adds delay, reduces the throughput that we can have. So this is a good solution, but like it paralyzes performance. Another huge problem is centralization. Although this one provider that we might have chosen, it's great and like hides our traffic from other entities, why are we trusting the provider in the first place? That's something like that I leave on you to decide. But the problem is that we really rely on those providers. So this leads to some centralization. And the most important thing is that we have no control. So we trust this provider that will route our traffic privately. And you'll hear me saying a lot of times no control, not because I'm a control freak, but just because it's important. It's your traffic, right? It's your traffic. You should be able to have a say on how it's really routed. Okay, so let's go to the network as a service. So this is another solution that has been more recently being more successful. In this case, it's like when you have cloud, you're kind of renting infrastructure for computing or for storage. In this case, you're kind of renting network infrastructure. So somebody else runs the network for you, and you might be renting some slice so that you can route your traffic around. And that's great. It's great for performance. It often happens that it comes with some security properties. So they might be also doing DDoS prevention for you, denial of service. They protect you from those type of attacks, or they might offer some VPN service potentially. But so it's somebody else running the infrastructure, and you're kind of using it. It might offer you some properties. You're paying for this. You're paying a lot. And you're again giving away all the control and all your trust to this provider that promises a bunch of stuff. And then we have the servers that are going close to the edge. I think this is the most interesting one because it's the most sneaky one. We don't really use it. Like if I ask you, are you using that? You would say no, most likely. But you actually are using it because you're using all these hybrid giants like Google and Facebook or Meta, whatever, and Microsoft, right? So every time you're using them, you're not going directly to their cloud, but you're going to the edge. So what they're actually doing is that instead they would have their own servers. They will put to your ISP, to your inter-service providers, and they will serve your traffic directly from there. So this is great for performance and reliability. In a way, they control everything, so they can optimize for everything. But it's expensive. Not everyone can do it. So like the hyper giants can do it, but not everyone can. There is some information leak because you're giving all the information to a single provider, everything. And of course, it leads to a ton of consolidation. Centralization, like it's at another level. And to understand how sneaky and how dangerous this is, I want to go through an example. So this is Google. Google has a lot of data centers. That's great, economy of scale. This allows us to use servers all over the world, and they're relatively cheap, and that's great. Great, okay. And they're like in different places of the world, everything is great. But that's not the full picture. In fact, Google operates a lot of points of presence. What are these? They're basically, they're trying to connect to the ISPs, and they do this in multiple locations in the world. So basically, this is the interface of the data center with the internet. So they have a ton of other machinery that allows them to optimize their network. Okay, that's great, good for them, good for networking people working at Google, good for us. But again, this is not the full picture. That's the full picture. And all these new ones that pop up, they're actually the Google servers that are in ISPs, in the internet service providers that we're actually using, and they're serving their clients, us, as close as possible. So this gives you an idea of the need for actually having super low latency and super good performance. This is why Google will go and put servers everywhere, servers that they operate, and they are actually hosted on the internet service providers. So they're expanding and they're going closer to their clients. And again, nothing against Google, all the hyper giants are doing similar things. So that's particularly interesting to understand the need, but you also, I hope, understand the risk. So like a different way of seeing Google's infrastructure is this. And by the way, this is their own information, like they advertise this. I don't know why you don't, yeah. It's a different ways of saying the same thing. So that's the data center, that's fair. They have their storage, they have compute, that's great. Then this is the point of presence, and then we have the edge. So this is how their infrastructure looks like, and that's great because they can serve their clients, so basically us, with high performance, high reliability, and low latency. Great. But of course, this creates a lot of industry consolidation. Not every company can actually do this, right? So if you're a new data center, you have amazingly good infrastructure, you have the best of the best servers, and you can do great things with machine learning. If you're somewhere in one location, you basically cannot compete with Google, not because you're not as good, but because your network cannot compete. You're not everywhere, you're just in one place. And low latency does play a huge role. So it's basically, this model gives no chance to smaller enterprises to flourish. They cannot compete, like, because such companies own everything. And then, of course, there is an issue also for regions, right? So even if we're fine with hypergiants, that's fine. But like, what about less served regions, right? Even the presence of Google or of Meta or Azure, it's not equally treated for different locations of the world. And that's problematic, right? So as an enterprise, why am I not allowed to use the internet? And should I like expect another company to come near me such that I can have reasonably good performance? This is super bad to think about. And of course, privacy risk, right? I don't really need to talk about it. Yeah, from the time that you send something to the browser, they control the network, they control it, and boom. Yeah, you don't really have data, by the way. All right, so can we do better? Like, can we actually not give up open public internet and allow the hypergiants to route all their traffic? Can we do better than this? I mean, at the end of the day, it doesn't look like a particularly hard problem, right? I mean, the internet is a graph. You can imagine the internet is a graph. Every time I'm sending a message, I'm sending something I'm trying to open a web page, I will be just sending one message from one node to the other in the graph. I do know there are multiple paths. So all I want to do is just measure the different paths and route my traffic accordingly, right? Should be fine. It doesn't, it's no rocket science. It's doable, right? Should be. It's not exactly as doable, even having very easy goals like low privacy, low latency, throughput and privacy. But why is that? So I hope I have motivated the problem, and now I'll talk to you about the challenges. Why is this question so hard to answer? So the first problem is BGP. So border gateway protocol. So this is the default internet routing protocol. It was designed decades ago. It works best. It works really well, but it's best ever, right? So because of BGP, although I'm a node and I know there are multiple paths, I'm not aware of them. Like these paths are not exposed to them, to me. And by the way, I will always be an enterprise, a small enterprise in the internet. Okay, so let's see a little bit more on how BGP works and why this is fundamentally hard. By the way, every time I'm saying something that you understand, please just interrupt me. That would be good. Okay, so let's say I'm this ASY. I'm actually cloud. I'm super good in terms of compute and storage. I'm super efficient. And I want people to be able to reach me very fast, right? So because that will help my business. All right. So I know that there is some part of the internet between me and every potential client. And for example, here you see this graph is composed of multiple autonomous systems, and yet you can imagine an AS as like AT&T or level 3, but of course they're much smaller ones, right? So we have a total of about 70K different SaaS ASs that compose the internet, right? But all of those small circles are actually networks that route the traffic. So my clients will not be directly connected to me. They will need to reach me via path. Okay, and BGP is responsible for finding me this path. Okay, so let's see how this works. So my AS, my internet service provider autonomous system, will create a BGP advertisement for me. So they expect to tell the world how to reach me. So this is what we call a BGP advertisement. There is a prefix. So everyone that tries to reach this prefix, this type of destination, they should contact this AS. And this BGP advertisement is basically propagated over the internet, following certain economic agreements. We won't go too low level than that. But what's important is that this advertisement is propagated such that all the ASs in the internet know how to reach ASY and my cloud. Okay, so let's again focus on this particular client. And then what we observe here is that ASX, although we do know, because we see the full picture, there are 3 paths, ASX will only see a single path, and that will be the one in the middle, because it has the least number of nodes. Is it the most performant? We don't know. Are those ASs in the middle good? We don't know. We just know that it has the least number of hops. By the way, BGP is much more complicated than I'm describing, and it will depend on which path is more economically, it's more cheap basically. So it's a cost-based protocol. But among routes, or among paths that have the same price, in a way, I will choose the one that is sold. If they're of the same, I'll just round it. But what's important here is that every time we have a destination, we will only learn about a single path to the destination, regardless of the path diversity. So here again, we have multiple paths, but ASX will only learn one path to ASY. Again, the advertisement goes the opposite way compared to the actual traffic. So first, propagate the advertisement this way. So the black arrows would be for the advertisement, and then the only advertisement that we will keep and the only path that we learn about would be the green. Okay, so all I want you to remember for all this is that BGP exposes a single path for every source to every destination. That's it. And this is independent of the reliability of the path, of the performance of the path, or of the security. So I hope I have convinced you that this is a hard problem. But even if I assume that I have solved this, and I can solve it by saying, okay, like this ASX, if it was a good client, it would actually have two internet service providers connected to it. So that's, and if that was the case, then they can actually choose. There's no longer there's a split brain situation here in which ASX actually has two providers. So now they can select the better path. Not the solution that we're suggesting, but let's say that's the case. So path diversity is not a problem. Do we have other problems to solve? Oh, yes, we do. And that's one of them is measurements. So you would have assumed that measuring the path, measurement, the delay between two ends, super easy. No, it's not, because there's noise, there's a lot of things going on the internet, right? So accurate measurements is actually super hard to do. Let's see a little bit why. So let's say that ASX wants to measure the delay of this path. We usually we will use tools like ping, for example. Ping, what it does is just it sends a packet and it expects a reply. That's it. But the problem with measuring like this is that we measure round trip times. So that means that we measure both the path to the destination and the path back. So when we actually want to make a decision on how to route, we basically select the single path forward, right? We don't select the path backwards. So if our measurements are basically merging the two, it's very hard for us to decide now. And also in terms of interpreting the measurements that we have, it's very hard because I don't really know if the delay that I'm observing is super large. I don't know whether that was caused from the path to the destination or back. So that's very, very, very hard for me to know. It's like very noisy. Another source of noise is actually the access network. The moment that the packet reaches the border gateway router, so the edge of the network, everything can happen. Like there could be a wireless link. It could be that the laptop of the ping is just like super congested at the time. The load is super high. So the delay is actually increased by random events that we're not interested in. We cannot avoid. Doesn't have nothing to do with routing. And they just adds noise to our measurements. So then if we want to do a control system on top of these measurements, good luck. There's no way, right? We have to trust the measurements, otherwise it's really hard for us. So that's why accurate measurements are in fact hard. But again, if I assume that I can do accurate measurements because I'm good enough, then I can do this. Trustworthy measurements. So far I was assuming noise as something that is random. So statistics can help us, like doing more measurements can help us. This is something that we kind of know how to deal with. What about an adversary, right? I never said that we trust anyone on the path, and we shouldn't, by the way. So what about trustworthy? What about this ASE? Let's say it's Eve, it's a malicious AS. It's aware that we're trying to optimize routing based on performance. And what they will try to do is that every time they see a ping, every time they see a packet that is expected to measure something, they will just prioritize it. So they don't have to improve their infrastructure. They just need to prioritize certain packets. And if this happens, then I will actually observe that this path is better. And then we'll route all my traffic through this path. Okay, if ASE is just interested in making fun of me and my stupid data-driven control system. But what if Eve is actually trying to attract traffic such that it analyzes it? That's super bad. We're basically moving traffic to an AS that would actually like play with our privacy. That's super bad. Or it could be that ASC is getting money for all the traffic that it routes. And that would have been fine if the performance of ASE is good enough. But if it doesn't, then it's really a mess. So what's important here is that we don't only care about the accuracy of the measurements, but they also need to be trustworthy. So we need to trust that when we measure delay, it was actually the delay of the path for every single packet that we send. Okay? And that's particularly hard to do. And the last challenge I had, assuming that I have solved everything else, is that, so I said that we're we're measuring, and it could be that ASY has all the knowledge of the paths, but in fact, ASX is making the decision. So my source, my client is making the decision about it. And if I were to just let them know of the different performance of the path, I would have to send all the data back to the source, and that will have a ton of delay, and I will also consume resources. So this is also a problem that somebody can measure and somebody else needs to make the decision with a split brain situation. So hopefully by now, I have convinced you that this is hard. Okay, so there are reasons why we didn't fix it ourselves, and we ended up with all these companies just selling something that the internet was supposed to provide, could provide. So, okay, so this is particularly hard, but basically nothing is hard if you have the right collaborators, right? So this is work that I have done with Henry Bricklet and Professor Jennifer Rexford. And recently, we're super happy to also have 2 more students. Jonathan is an undergrad, and Benji is a master's student at Princeton. So with this amazing team, we're doing great. I will explain how we solve all of those challenges, and also where we are at. So, like, what are our next steps? What do we want to see Tango achieving? But before this, I will explain what Tango is. And I will claim that all the challenges that I have explained before, we're solving all of them. And we're solving them with just a very simple, elegant idea. So, because the two, like, if we have a single network that tries to optimize their performance, that's very hard if it's alone, right? But if there are 2, they can collaboratively solve all those challenges. For example, let's take the BGP problem. So we said that ASX, which is the provider of the cloud, would actually advertise it will create a BGP advertisement, and that will result in ASX only learning a single path to a single destination. But what if ASX and ASX and ASY, they collaboratively decide that, you know what, we're no longer one destination, but we're many, we're 3, as many as the paths. So if ASY creates multiple BGP advertisements, and we make sure that those advertisements are independently routed over the internet, then ASX actually sees multiple paths to different destinations, virtually different destinations. So if you notice, the prefixes that I have here are different. But in fact, I have agreed as ASX with ASY that this is in fact the same thing. We're just using it to use different paths. Again, I have kind of hide a lot of the details. So in fact, you need to use BGP poisoning or communities or a ton of things. But what's important is that if they collaborate, ASY can expose paths to ASX, such that when ASX routes traffic, they can change the IP destination of the packets and effectively change the path that they're taking, right? So we're not really changing BGP. We don't require anyone in the middle to play with us or BB9, but we're still managing to get access to multiple different paths. That's great, I think. Okay, so that's the first, like, we managed to get path diversity. It's super nice. So we control, now we can select which path each packet will take. But actually I had a lot of challenges, right? So what about accurate measurements? I have not done anything about it yet, right? So the fact that I control which path the packet will take doesn't give me that. But the location that I am actually helps me a lot, because I actually don't need to measure all this. Naturally, as a pair of Tango nodes, we're actually at the border of each network. So the access, we don't really measure. We measure from this border gateway router to the other. So this is what we call edge to edge. And the second thing that we have is that we can do one-way measurements. Because we're now 2, we're not a single node that tries to ping and has to measure round-trip times. We can actually measure just one way, right? Because ASX can send a particular packet to ASY and we just measure the difference. So like, let's say we have these 3 packets, it's saying the destination IP such that we are able to use the different paths, and we add to those packets the timestamp at which they left ASX. So upon arrival on ASY, ASY knows the current time, so they would know the delay, the difference between when they arrived and when they left. That's really easy. So we have one way, we have edge to edge, and we have real time. How do we have real time? Okay, so you see this P4 there. So this is the fact that we're actually using programmable data planes. This is a special type of device that allows us to program it. And also it has memory, like, so we can store, we can keep statistics on the data plane. So because of these 3 things, the fact that we're sending timestamps, so we can have one way, we are at the border gateway, so we don't have the access network, and we're using these programmable data planes, we can actually achieve one way edge to edge and real-time monitoring, which is accurate monitoring. And of course, we have to deal with a ton of challenges on using the actual hardware because it has a ton of constraints, and the memory is limited, and the instruction set is limited. We're fine because we actually managed to have accurate measurements, which is very important. But accurate doesn't mean correct, because we can have an adversary. So a very simple example would be, okay, we have this ASE, which is actually evil, and every time it sees a packet, it will just add something to the timestamp, such that when ASY receives this packet, they will assume that it left later, so that the delay is lower. So here, although we are adding this packet to every single, we're adding the timestamp to every single packet, so ASE has no way of differentially treating any packets, preferentially treating any packet. They can still just change this, right? So the way that we go about solving this is that we have the 2 ends sign the message that they send. And I understand that this is old news and this is like super boring because this is a common thing that we do in security, but I want to stress that we're actually doing this from 2 networking devices, 2 switches with very limited memory and very limited instruction set. So it's actually very hard to do. And in particular, what we leverage to achieve this is a couple of observations. One is that timestamps are expected, like it's 1, 2, 3, 4. It will not be 1 and then 7 and then 2, right? So we know the sequence, and there will be packets all the time. So we know that all of them will be used. So one great thing is that we can basically pre-compute the signatures because we know how the timestamps are expected to go, right? Another important thing for us is that, okay, so we only care about millisecond difference. If it's microsecond, we are anyway in the internet, it will never do that correctly. So, so we limit the types of messages we have. And another observation that they're actually using is the fact that an adversary, if they learn a mapping between an older timestamp and now, and the signature and the actual packet, that's not useful. Because we don't care about an attacker trying to expose their path being worse than it actually is. This they can anyway do. They can just start dropping paths. I mean, this is fine. We just want to prevent an attacker from persuading us that a path is better, has lower delay than we actually measure. All right. And the last thing, it was about real-time control. So the problem here is that all the statistics, all their delays for, in our case, are in ASY, but actually ASX needs to make the decision. And sometimes these needs to be real time. So because of consistency, a lot of applications, they actually need consistency. So the way that we decided to deal with that is that instead of ASY having to send back all the data and allow ASX to recompute their objectives and decide, we're actually trusting ASY to send only the routing information. So instead of asking ASY to send the full data, we're just asking them to send the output of the objectives of ASX to back to ASX. All right. Okay. So by now, I hope that the name makes sense. So we call our architecture Tango because it really is close to what Tango is about. So in this picture, we see two people that they're dancing. One is based on the way that they stand. It's clear that one is the follower, the left person is the follower, and the right person is the leader. And the way that Tango basically works as a dance is that you have to signal the moves. There's no choreography, right? So one partner needs to signal different moves, and this is in a way that is graceful and nobody can understand it, and it looks like a flowing, right? In a similar way, we have our sender switch and our receiver switch, and the sender switch performs the actual moves, so they select the path, but is what the receiver has already signaled. So we need two ends such that they can dance, and one signals the other, and this is how we select the different paths according to the objectives that they have. All right. So that was all great, but I mean, if we don't have any data, I understand that you will not believe me about anything. So it's really important that we have very good, actually our results are much better than we anticipated. Because every time you're talking about internet routing or even on networking, people, they'll immediately jump and say, oh, this is an old problem. People have looked at it and we have all the hyper giants. And what can you do better than Google? And that's true, I agree. But actually we did better. So this is our setup. This is our preliminary setup. This is actually a couple of months ago. It has we have done better now. But like I think this conveys the message that I want to give. So here we see our setup. Basically, we use Vultr. Vultr is a data center. It's a relatively smaller data center. I guess not everyone here has already heard about it. So we were not special clients. We were just regular clients. We didn't do anything fancy, right? We just basically host two VMs. We ran two VMs, one in Los Angeles and the other in New York. And we basically, Vultr by its own allows all clients to talk PGP to the router that Vultr used. So what we did is that we advertised different IPv6 prefixes such that we can expose multiple paths. And we actually did expose multiple paths. And by the way, I want to stress here that was Henry. I didn't run any of that. So what Henry managed to do is really exposing multiple paths using these special advertisements. And again, we don't have any special treatment either from Vultr or from the rest of the internet. And still, we managed to expose multiple paths. That means that we can actually, by changing the header of the packet, we can select which route we'll take. But this would only be useful. I mean, it's great that we can control the path, but is it useful? Would it give us better performance? And it actually does. Although it's like, as you can see, just a single hop. So the length of all the different paths is almost the same. Only one has two hops. And all of these ASs are actually super known. So you would expect them to have perfect infrastructure and no real difference between each other. Well, actually, that's not the case. So in this graph, you see the latency measured in milliseconds of the different paths as a function of time. So as you can see, the different colors correspond to different paths that traverse different ASs, different internet service providers. And as you can see, there's quite some difference among them. And can you guess what was the BGP default one? Like lower is better. So I can tell you already that the green one was the best one. But what was the default one? Yes.
NTT.
Correct. So the worst one was actually the default one. Which is interesting because obviously like 30% higher delay is what you get if you were just using BGP as opposed to Tango. And again, you're not any special tenant in the internet or in Vultr or anywhere, right? This is with minimum infrastructure, which is great. All right, like networking people are a little bit more less likely to believe you, which is fine. So this is like more time. And the comment here is that, okay, we see that the green one is better, but like, is it better all the time? Or did you just select these 45 hours where that was the case? And we ran it for longer and we basically observed that it's true. Sometimes we have some instability in this particular network. It could be something that just happened once within like months, but we caught it. And what's clear is really important that there is a path that is still better than the default one that is super stable, right? So if we were to have real-time monitoring, we will not have to pay the price for this increased delay of the green line. Clear? Sound clear? All right. And so far it was great, like super exciting. Like everything there, the research, the people, that's great. But there are a lot of things to do with this. So this collaborative changing of paths, this has a lot to offer, much more to offer than we have done so far. And the first thing that we're very interested in doing is actually using this for privacy. So I kind of hinted at privacy, but I didn't deliver. I'm sorry for this. But like, it's something that we are actively thinking about. And that's because we're in a great location. We are in a location where we can change the path. We can be protocol agnostic, and we can still provide some privacy by reducing the amount of traffic that each single AS sees. This is really important. Every time we're trying to do website fingerprinting, the attacker would actually need to see a lot of traffic to understand, or some amount of traffic to understand what this website is, or infer anything about it. So by reducing the amount of traffic that each AS individually sees, we can reduce how exposed we are in such attacks. And the fact that Tango can do it very fast, also taking performance into consideration, is great because we're not giving away anything. Another thing that we're very interested in and excited about is trying to incorporate multiple different objectives. So like we are kindly like, in our own circle where latency is important and throughput is important, but we're not really aware of particular other objectives like geofencing or how would this look like. So this is something that we're very excited in trying to understand. So what would be other objectives that people would have, and they never really talked about them because that was not possible, and Google cannot provide it. Another thing that we're very excited to start working on is, okay, so we basically can change our path, but this is a control system, and every control system needs to deal with oscillations. What happens if, the performance looks best in one path now, and then another path later, and another path later? Super bad. We need to make sure that stability is there. And then, like a more fancy or like long-term vision that we have for Tango is that we actually want this to be an overlay network. So the moment that you're sure that your two ends can collaboratively optimize for performance and privacy and security, name it, you can actually build your own overlay. And if you can make it such that every new node that joins will not have to have a huge investment, then you can actually start building an overlay network that can be used by other applications offering those objectives. Of course, you have to solve another ton of challenges there because permissionless needs a lot of care, but this is what we have in mind. All right, so in the end of my talk, I just want to recap. If you forget everything and me and everything you ever had, like, I want you just to remember those things. Applications need performance, they need privacy, they need security, more than ever. And the internet is not up for the task. So paid solutions are there, but they are actually hurting because they enforce consolidation. So Tango, which is a two ends opt-in approach, has some very interesting properties for this. For example, it exposes path diversity, it allows accurate and trustworthy monitoring, and it also facilitates real-time control of the internet paths. And maybe also this picture that would be nice. But that's it. All right, thank you so much.